Hey guys, Anthony Santa from myrecordinginternship.com here with a presentation on how your plugins work. Today we're going to talk about compressors. We're going to get deep into it. We're really going to understand the calculations being made and what's happening, how your compressor reacts, and how you can better use it. All right, so here we go. So compressors are dynamic processors. Dynamic processors meaning it affects the volume. Here are the few things we need to know in order to get started in our process of understanding compressors. We need to know input volume. So volume or gain just means change of volume. So when people ask you to adjust the gain, that just means raise it or lower it, in decibels. You want to 1 decibel up, 1 decibel down, that's a gain adjustment. So volume before the plugin is used is your input volume. Your threshold, that's the point at which the compressor will engage. Your ratio is the mathematical rate at which the gain reduction will be calculated, and we will get into this. We're going to get into it. We're going to make it real simple, okay? Your gain calculation is, we're going to take the ratio and the threshold and do some gain calculations, but basically what it is, it's the gain value change. It's how the value changed from input to output, and then when you send it to the output, that's your output volume. So what is the new volume after it goes through the compressor? You could also make gain adjustments at that stage in most compressors as well, but let's get into it now. First, we will have to talk about graphing. I'm going to make it simple, I promise. Just follow along with me here. Assume that your input volume is represented by the letter X. Input volume equals the letter X. To graph this as a function in which we can use to find gain and or gain reduction, we'll need 2 axes basically. We need an X-axis and a Y-axis. So we need X being the input and Y being the output. So the Y-axis will represent what comes out of the compressor. So our output volume will equal Y. Now we're going to graph all possible values without any compression. So your input is going to be equal to your output. And we said that X is your input and Y is your output. On this graph, X is the horizontal line. That is X. And on this graph, Y is this line right here going vertically. Okay, so this graph is Y equals X. It's really that simple. All your output and your input are equal to each other. Really, really simple. So the output Y is equal to the input X. Now we can include the number variable N. This is where some people get a little lost because it starts to look like algebra here. Y of N is equal to X of N. The number variable just means any number. So any number N will be equal to X. All of them will be equal. So right here, you can see -1 and -1. Yep, they're equal. And +1, yes, that's equal too. So when Y is 3, X will also be 3. So if we try to find this on the chart, so Y of N would now be Y of 3 is equal to X of N, X of 3, which 3 and 3. And we see right there, the red dot is where they intersect. Now we want to graph a volume change. Now we have decided to raise the volume 1 decibel. We just made a gain change. You could go up and down with this. We're just going to go up 1 decibel for this example. Our new graph is represented by the function Y equals X plus 1. A volume change will move the graph up or down by an equal amount to that volume change. If the input volume X is 3, the output volume will be 4, because X plus 1 equals 4, 3 plus 1. Solving the output volume of a 3 decibel input. Y equals X plus 1. We want X to be 3, so Y equals 3 plus 1. We solve it, Y equals 4. So X is 3, Y is 4. Our output is 4 when our input is 3, according to this function. All right, so now let's get into our compressor and why I just went over all of this. Finding the output of your compressor, we're going to use graphs just as well. Before reaching the threshold, Our graph is the first graph we looked at, that y equals x graph. So whatever the input is, the output is. There's no compression being done. Input to output will have no effect at all. Now, we will look at the output of the compressor and find the compressor output after compression is applied. A 1-to-1 compression ratio allows a signal to continue on the path y equals x, even after reaching the threshold. So 1-to-1 means there's no compression being done. It's a pass-through of the signal. Now, what if it's not a pass-through of the signal? In our example, our threshold is set to 20 decibels. Okay, so input from 0 to 20 decibels will have output equal to that input. So y equals x from 0 to 20 decibels, and then after that, we start applying compression because that's where our threshold is. And our threshold shows us where compression will begin to be applied. A compression ratio of 2-to-1 will result in the output being divided by 2 for each decibel over 20. So after we reach 20, now we go to 21, 22, 23, 24. Now each one of those decibels is going to be divided by 2. So you're only going to get a half of the decibel change that actually happens. So if it goes up 2, it actually is going to get compressed down to only have gone up 1. Just 2 divided by 2 equaling 1. So let's use some simple math to find an output. Ratio at 2-to-1. Here's the example. We're going to assume an input volume of 40 decibels. So we have our equation here. We know threshold is at 20. So we want x minus 20 divided by 2, because anything up to 20 will not be compressed at all. It'll be a pass-through signal. And that'll be equal to y minus 20. What we do to one side, we have to do the other side of the equation. Some basic math stuff, and you'll see how this equals itself out. Now, if we put 40 in where x is, because we're assuming the input volume of 40, we have 40 minus 20. That has to be done first. That's what the brackets are for. Then divided by 2 equals y minus 20. Let's simplify this. 20 divided by 2, our ratio of compression, equals y minus 20. Next, 20 divided by 2 equals 10. So 10 equals y minus 20. Now we will add 20 to each side of this equation. So if we add 20 to the side with y on it, we just get y, because there's a negative 20 there. So plus 20, we just get y there. On the other side, we have 30, because we added 20 to 10. So y equals 30. Now we have an output of 30 decibels, meaning that we have a gain reduction of 10 decibels. So your compressor has an output. After you do all of this, your compressor will have an output for this signal at 30 decibels instead of 40 decibels where it actually was sitting before it hit the compressor. Now, one more ratio example, and they're all the same, all these ratio examples. We're just going to do one more just to make sure we drill this home. So just watch here. Assume our input volume x is 40 decibels. X minus 20 over 4. 4-to-1 ratio means over 4. We need to divide by 4. Is equal to y minus 20. Or 40 minus 20 over 4 equal to y minus 20. So we divide first. We subtract first. We have our 20. And then we divide that 20 by 4. And we still have on the other side y minus 20. Now we have 5 equals y minus 20. We add 20 to each side of this equation like we did on the other side. We get rid of the negative 20 on the y side. And we wind up having 25 on the other side. So y equals, your output equals 25, meaning we have a gain reduction of 15 because we started with 40 decibels. So this is the very, very basic math, and it's going to get a little bit more complicated, but we won't really need to dig into all of the small, minute things now that you understand how this is working. I'm going to show you the other functions on your compressor and what they're doing to change this. All right, the rest of the basics. Our compressor is currently working on a sample-by-sample resolution, meaning every sample is getting compressed right away. That's the only way this math works out. So it's reacting immediately. This compressor reacts so quickly that it would work towards evening out our instrument strum or stroke, kind of like the attack of our instrument when we hit it, and our input instrument's sustain. So say we're strumming a guitar, we want to have a nice big loud strum and it'll soften itself out because that's natural and that's what's real. So we want to keep the dynamic range of that. We want there to be a bit of a attack from your instrument, a big of a strum or stroke. We want that transient to be big there. So this is where attack time, release time, and knee come into play. Attack and release. Attack time is the amount of time the compressor waits before reacting to an input. An attack time of 100 milliseconds will cause the compressor to wait 100 milliseconds before compressing the input. Release time is the amount of time the compressor waits before allowing the input signal to pass through without compression. So the compressor goes down after 100 milliseconds, and if we set the release time at 100 milliseconds, the compressor won't release until after 100 milliseconds. So you'll get your gain reduction going on, and it will last 100 milliseconds after the signal has come through that caused the gain reduction to happen in the first place. All right, we'll explain this a little bit more. Attack and release simply allow for smoother compression. If an attack time or release time is too fast, it may cause the signal to sound over-compressed. This is due to the compression kicking in at the start of the transient. You can tell that the attack is too fast when the strum of an acoustic guitar is almost as loud as the sustain from that strum. If an attack time or release is too slow, it will allow for volumes outside of the new dynamic range attempted to be established by the compressor. So that just means that some inputs will go uncompressed, while some inputs will feel compression that they don't deserve. So what'll happen basically, some inputs will go completely uncompressed because it takes so long for that compressor to kick on that it goes up to exactly how loud it was. So if we were at 40 decibels, that one hit 40 decibels and we got no compression on it at all. Now, if it took 3 seconds to react to that, now we strummed that guitar, we hit 40 decibels, it started going down and it took 3 seconds to react. By that time, the signal might be low and under the threshold. So we're pushing now a signal that's way, way lower. Maybe it's at 10 decibels, and we're going to push that sucker down a whole bunch, and we're creating a larger dynamic range by doing this. It's something that we really, really don't want to do. So you can be too fast on the attack, and you can be too slow on the attack, and these are the reasons. Now, a knee. Here's how a knee works. Compression can be slowly applied using a knee. A knee will allow the compression to be applied over time rather than all at once. And you can kind of see that in the graph. There's a hard knee at the top, which has an angle on it, like a real strict angle. And there's another one that has a curve. That's a soft knee. So a hard knee results in similar outputs to the ratio examples that we spoke about. And the soft knee uses interpolation in order to allow the compression to take place at different ratios along this curve. So all that means is that there's a curve here and there's different ratios of compression being applied along the curve. And then once we get outside of that curve, we go right back to the original amount of compression like we discussed first and we did those equations about. Now, the knee width is going to basically show us where that compression, that original compression is allowed to be applied strictly and where the curvature starts. So it's simply a decibel range where the knee applies. So if we have a knee width of 10 decibels and a center at 20 decibels, we'll cause compression to happen along that curve, that slope, for inputs ranging from 15 decibels to 25 decibels. So this would be here 15, and this here would be 25. That's our curve amongst a 10 decibel range centered at 20 decibels. This allows compression to be rolled on and off. The term rolled, it kind of makes sense for this. Since it's kind of like more of a slope, you think of rolling on and off. It doesn't just hit it hard. It's not a strict compression. Okay, compressions causing distortion. This is something I added to this because you will wind up with this problem as you do your really, really fast attack and release times. The distortion you're hearing is coming from the low end. A cycle for a low frequency audio wave can be no longer than your attack and release time. Frequency in hertz is simply the amount of cycles that signal does per second. So a 20 hertz sine wave does 20 cycles per second, or 1 cycle per 50 milliseconds. So if you are now allowing this attack to attack it at 25 milliseconds, and you're allowing with your EQ or something 20 hertz to be seen and heard, you don't have any sort of filtering on it, you will have distortion happening around there. So why does this cause distortion? As a compressor attacks and releases inside one cycle of a sound wave, that wave can change shape. Wave shaping is seen in distortion code. Digital distortion code can be written very, very simply if the goal is simply distortion rather than amp modeling, which gets a little more complicated. But this is what's happening. You're having basically this wave shaping going on that sometimes makes for asymmetrical signals, which will cause you distortion. It just absolutely will. I have an example of a distortion code here. If you take a look at it, if you understand it, that's great. You can graph this, put it in a graphing calculator or something and take a look at what it really looks like. But N in this equation is the signal being processed, and K is the amplitude controlling the nonlinear processing. So you'll need to look at this, and I'm not sure if you're going to get into actually making a distortion plugin, and this is probably not the best way to make one anyway. But this is what's happening when you go ahead and you apply your compression faster than a cycle of the input. So the code example was brought to us by Designing Audio Effects Plugins in C++ by Will Perkle. Great book. I have it. I've read it. If you want to learn about making plugins, I do suggest it. And if you want to talk more about making plugins, we could go over that too. So I really hope that this helped you get a view of what compressors are actually doing and how you can use them to compress your signal. All right, thanks for being with me on this one, and I hope to see you on the next one.